Example 1. Assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 5 feet per second. How fast is the area of the spill increasing when the radius of the spill is 45 feet? Start off by drawing a diagram with a circle. Label the radius, and the area is pi r squared. Take the derivative of the area. So the derivative of A is 1 times dA over dt. And then the derivative of pi r squared is 2 pi r times dr over dt. And then the derivative of delta over dt is what we want. And what we have is the derivative of the radius over dt, which is 5. Then we plug in dr dt into the formula, and we get 2 pi r times 5, which ends up being 10 pi r. When we try and find dA dt, we just plug in 45 for the radius, since the radius of the spill is 45 feet. So we get 10 pi times 45, which equals 1,114 feet squared per second.
Example number 2. A softball diamond is a square whose sides are 60 feet long. Suppose that a player running from first to second base has a speed of 25 feet per second at the instant when she is 10 feet from the second base. At what rate is the player's distance from home plate changing at that instant? First you draw your diagram, you draw the softball diamond, you draw the player running from first base to second base, and the distance from home to that is z. The distance from the player in second is 10 feet, and the distance from the player in first is 50 feet, which is the x value. And the distance between home base and first base is 60 feet, which is known as y. Next you set up your problem, which is x squared plus y squared equals z squared. You know that dx dt is 25. You know that dy dt is 0, and you want to know what dz dt is. You want to know that. So you find the derivative of the whole thing, which is 2x dx dt plus 2y dy dt equals 2z dz dt. Since you know what you have over here, you plug it in, which is 2 times 25 plus 2 times 0 equals 2z over dz dt. Once you combine like terms, it's 25x over z, which equals dz over dt. You plug in what z is, which you find out is that, which equals 25.5 over 10 times 60 root of 61, which is approximately 16.0 feet per second.
Example 3. A camera is mounted at a point 6,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at 700 feet per second when it is 8,000 feet above the launching pad, how fast must the camera elevation angle change at that instant to keep the camera aimed at the rocket? So you draw a diagram, the rocket here, and then the camera here. And then the distance from the camera to where the rocket was launched is x. this angle is theta. It's a right triangle. And the angle from the ground to the rocket is y. And then we're trying to find this angle, so then the tangent of theta, which is opposite over adjacent, is y over x. So you take the derivative of that. And then the derivative of tangent theta is secant squared theta, d theta over dt. And then the derivative of y over x, you do low d high minus high d low over low squared. So you get x times dy over dx minus y dx over dt all over x squared. And then we know that d theta over dt is what we want, and dy over dt is 700, and then dx over dt is 0. So then you multiply each side by 1 over secant squared theta to get the d theta over dt by itself. And once you plug all these numbers in, you get d theta over dt equals 6,000 times 700 minus y times 0 all over 6,000 times cosine squared theta, which is the same as 1 over secant squared theta. Then when you simplify all that down, you get d theta equals over dt equals cosine squared theta times 7 over 60. So then to find theta, you do when y equals 8,000, since we're trying to find when the rocket is 8,000 feet above the launching pad. Tangent of theta equals 8,000 over 6,000, and then theta equals tangent inverse of 4/3. So then to find d theta over dt, you get theta is tangent inverse of 4/3. So then you plug that in to the cosine squared theta, which is tangent inverse of 4/3 times 7 over 60. And that ends up being 0.042 radians per second. And then to convert that to degrees, you do 0.042 times 180 over pi, which ends up being 2.41 degrees per second.
Example number 4. Grain pouring from a chute at the rate of 8 cubic feet per minute forms a conical pile whose height is always equal to the diameter. How fast is the height of the pile increasing at the instant when the pile is 12 feet high? First, draw your diagram, which is just going to be a cone. Which the volume of a cone is V equals 1/3 pi r squared h, which is the height. The radius, so r squared, is also known as half of the diameter, so you can plug in d over 2 squared times h, which the diameter is also equal to h because you want to get one variable, which is h now. So volume equals 1/3 pi over h divided by 2 squared times h. Once you combine all the like terms, which is if h over 2 squared is also known as h squared over 4, which is then once you combine like terms equals 1/12 pi times 3 or times h cubed. You want to find the derivative of both sides, and we know that dv over dt is 8, and then the derivative, you want to get all like terms on one side, so you bring over 12, so you multiply it by 12, and you divide it by 3 because of the derivative. And that equals pi h squared over dh dt. Then to add that to one whole number is 32 equals pi h squared times dh dt. You need to get dh dt by itself, so it's 32 over pi h squared equals dh dt. And back to the problem up top, we know that h is 12 feet, so then you plug in the h, which is 32 over pi times 12 squared, which equals 0.071 feet per minute.
Example 5. A stone dropped into a still pond sends out a circular ripple whose radius increases at a constant rate of 3 feet per second. How rapidly is the area enclosed by the ripple increasing at the end of 10 seconds? So start out by drawing your pond. There's the radius, which is r. And then the area of that pond is pi r squared. You want to take the derivative. So then the derivative of a is dA over dt. And the derivative of pi r squared is 2 pi r dr dt. We know that dA over dt is what we want. And we know that the dr over dt is 3, since the rate of change is 3 feet per second. So then when you plug in 3 for dr dt, you get dA over dt equals 6 pi r. We know that the time is 10 seconds. So then to find r, we plug in 3, which is the rate of change, times 10, so we get 30. Then to find dA over dt, we plug in r back into this equation here, and we get 6 times pi times 30, which ends up being 565.49 feet squared per second.
Example number 6. A 10-foot plank is leaning against a wall. If a certain instant the bottom of the plank is 2 feet from the wall and is being pushed toward the wall at the rate of 6 inches per second, how fast is the acute angle that the plank makes with the ground increases? First, draw your plank against the wall. So you're drawing a triangle. Here's theta, this is y, and that is x. You set up, referring back to SOHCAHTOA, you know that the adjacent hypotenuse, so adjacent is y, and hypotenuse is x, which is cosine. So you plug in the formula, which is cosine theta equals y over x. First, you need to find the derivative of that, and we know that the derivative, so d theta over dt, we want to know. dy over dt is negative 0.5, and we know that dx over dt is 0. So once you find the derivative, you plug it back in, so the derivative of cosine theta is negative sine theta d theta over dt, which equals, you use the low d high minus high d low over low squared formula, which is x dy dt minus y dx dt over x squared. So you plug in from what you know, and you get negative sine theta d theta over dt equals 10 times negative 0.5 minus 0 over 10 squared. Once you combine like terms, you get d theta over dt equals 1 over 20 sine theta. Referring back to the original diagram, you plug in from what you know from the problem, which y is 2 and x is 10. So then for theta, you're going to plug in cosine inverse of 1/5, and you plug this back into that above problem, which approximately equals 0.051 radians per second, which you need to convert into degrees, which equals 2.92 degrees per second.